A few weeks ago, one of the most basic assumptions in all of cosmology was declared broken. A team of astronomers looked at a massive new data set, over 1 million galaxies, and found something that shouldn't exist. Structures so large, stretching so far, that they seemed to defy one of the founding rules of the universe itself. If they were right, it meant our entire model of the cosmos needed to be rewritten. But was it actually right? Let's find out what happened next. So what actually is this founding rule they broke? It's called the cosmological principle. It's the idea that if you zoom out far enough, past galaxies, past clusters, past filaments, the universe looks the same everywhere and in every direction. No special spot, no special direction. Just a smooth, uniform cosmos on the largest scales. Think of it like stirring milk into coffee. Right after you pour it in, you can see swirls and streaks. Some parts darker, some lighter. But wait a few seconds and it blends into one uniform color throughout the cup. Cosmologists have long assumed the universe works the same way. Zoom in close enough, a galaxy, a cluster, and you'll find plenty of structure. But zoom out far enough and it's supposed to blend into that same smooth, uniform color in every direction. This isn't just a nice assumption, it's the bedrock underneath the entire standard model of cosmology. The lambda CDM model that explains everything from the Big Bang to how galaxies formed. So when physicists Francesco Sylos Labini and Marco Galoppo published a paper in Nature analyzing the DESI DR1 galaxy survey, one of the largest 3D maps of the universe ever made, and reported coherent, aligned structures stretching across gigaparsec scales, cosmologists paid attention. And DESI itself is worth pausing on for a second, because the scale of it is hard to overstate. This is an instrument that has mapped tens of millions of galaxies, reaching back across roughly 11 billion light-years of cosmic history, one of the largest 3D surveys of the universe ever assembled. To actually test for this kind of hidden pattern, Sylos, Labini, and Galoppo didn't just count galaxies at different distances. They looked at pairs of galaxies separated by the same distance, say 500 million light-years apart, and asked which direction those pairs tended to point. If the universe really is the same in every direction, those pairs should point every which way with no preference at all. But when they ran this test on the real DESI data, they found an excess of pairs lining up along very specific directions, forming what looked like coherent filaments stretching across the sky. Gigaparsec scales, that's billions of light-years. Structures that big, that aligned, aren't supposed to exist in a uniform universe. If confirmed, it would mean the universe has a kind of grain to it, a texture, at scales where it's supposed to be smooth. But here's the question that should always come up when a single paper claims to overturn decades of established physics. How do we know they're right? That question didn't take long to get an answer. Within about a week, cosmologist Till Sawala at the University of Helsinki posted an independent analysis of the exact same DESI data. And what he found was different. Sawala didn't dispute that the raw data showed something. What he questioned was how the original team measured it. Here's the thing about a universe that's expanding. Distance isn't as simple as it sounds. There are actually multiple ways to measure how far away a galaxy is, and they don't agree with each other once you're talking about billions of light-years. So which one did the original team use? And did it matter? It mattered a lot. Sawala found that Sylos, Labini, and Galoppo had measured galaxy distances using something called luminosity distance, when the correct measure for this kind of analysis is co-moving distance. These aren't interchangeable. Luminosity distance accounts for how the light from a galaxy has stretched and dimmed on its way to us. Co-moving distance strips out the expansion of space itself, so you're comparing galaxies as if the universe had frozen in place. For nearby galaxies, the difference is tiny, but at the scales this paper was working with, billions of light-years, the two measures diverged dramatically. Here's another way to picture that mix-up. Imagine two people trying to describe how far away a mountain is. One measures using a photograph, how small and hazy it looks through the atmosphere. The other measures using GPS coordinates, the actual straight-line distance, no haze involved. Both numbers are correct in their own way, but they don't match, and the gap between them gets bigger the farther away the mountain is. That's essentially what happened here, except instead of a mountain, it's a galaxy billions of light years away. And instead of haze, it's the expansion of space itself stretching the numbers apart. On top of that, the original team hadn't properly scaled their distances to account for how fast the universe has been expanding this whole time. Put those two mistakes together, and you get an error factor of roughly 1 plus the redshift divided by the Hubble constant. That sounds abstract, but here's what it does in practice. It takes structures that are actually a normal, expected size and makes them look enormous. Structures that fit comfortably inside the standard model suddenly look like they're breaking it. Sawala reran the numbers using co-moving distance and then compared the corrected data against simulations from Flamingo, a major hydrodynamic simulation built entirely within the standard Lambda CDM framework. The result? The anomaly disappeared. The structures lined up with what Lambda CDM already predicts. So was this a fringe objection nobody took seriously? Not exactly. Here's where this story gets more convincing, not less. And it wasn't just Sawala raising an eyebrow. Even before his rebuttal came out, cosmologist John Peacock at the University of Edinburgh had already pointed out that the claims seemed to conflict with much of what's already known about large-scale structure, including conclusions drawn from that very same DESI dataset. His view at the time was that a result this disruptive would need serious corroboration before anyone treated it as settled. Sylos Labini, the original author, didn't dig in and defend the paper. He acknowledged the distance measurement error and said he and his co-author were redoing the analysis. He did note that Sawala's approach leaned more on the patchiness of large-scale structure than on its orientation, so the door isn't fully closed on every part of his original claim. But on the core mistake, he conceded the point. And this wasn't just one scientist's opinion floating around online. The correction was covered independently by Science, by Scientific American, and by other outlets, with other cosmologists weighing in that the original claim looked shakier the more it was scrutinized. Sawala himself put it simply: the more a claim flies in the face of expert consensus, the less likely it is to survive expert scrutiny. So, does that mean the universe is boring? Just smooth and uniform everywhere, case closed forever? Not quite. And that's actually the most interesting part. This isn't really a story about one paper being wrong. It's a story about how the cosmological principle keeps getting tested, hard, and keeps holding up. The Lambda CDM model isn't fragile. It's been stress-tested against exactly this kind of claim before, and it survives because when someone finds a crack, other scientists immediately try to break it further or explain it away. That back and forth is the process working correctly. And this wasn't even an isolated incident this year. Just a few weeks before this, a completely different team made an almost identical kind of claim, that one about dark energy, arguing the universe's expansion might already be slowing down instead of speeding up. I actually covered that one in a previous video, if you want the full story. But the short version is, that claim also got picked apart within a matter of months, for a strikingly similar reason: a measurement mix-up that made an ordinary result look like it was breaking physics. 2. The universe is broken headlines, 2 math errors in the same year. And there's a bigger reason this matters beyond cosmology bookkeeping. The cosmological principle is part of what lets us assume the same physics applies everywhere in the universe, which is also part of the reasoning behind why we expect the same conditions for life, the same chemistry, the same physical laws, no matter where we're looking. If the universe genuinely had a hidden grain to it at the largest scales, that assumption would need to be revisited too. So next time you see a headline claiming physics is broken, the real question isn't, is this exciting? It's, did anyone check the math yet? If this is the kind of story you want more of, not just new discovery, but here's what happened when someone checked, that's exactly the kind of science story worth following closely, because it's usually where the real understanding shows up.